What's going on everyone, this is Jay Patel and in this video we will be deriving the equations for the backpropagation for multi-class classification. In the previous video we derived the equations for the binary classification, and if you have watched that previous video then you will know that we came up with these equations for the binary classification. Now if you haven't watched my previous video yet, then make sure to check that out first, because I have provided the complete mathematical details behind the derivation of these equations, so make sure to check that out. And if you're new to this channel, then make sure to check out my neural network playlist, because I think I have provided the best possible explanation for neural networks, along with all the mathematics behind it and the intuition behind it. I will provide all these links down in the description box, and you can also find it by clicking in the upper right corner. Also, before moving forward, this is your chance to hit the red subscribe button and also hit the bell icon so that you get notified every Sunday I upload a new video. And without taking further time, let's get started with this video. Now for multi-class classification, only this term dz3 is going to be different because this dz3 depends on the loss that we used and the output activation function a3, while all these rest of these equations just depends on this dz3. So all these equations are going to remain the same for multi-class classification as well. So in this video we will only focus on deriving this dz3 for multi-class classification. And as we are just calculating this dz3 in this video, I will omit writing this 3 every time, and I will just write it as dz, which is dl by dz. And this L is the loss for one observation, which is given by this equation, where here n is the number of neurons in the output layer. So our output layer can have as many neurons. For example, this can be A1, A2, and it can go up till AN. And the values of these neurons can be given by this equation, where this equation is nothing but we are just passing the z's, the different z's, to the softmax activation function. Now this dl by dz can be split into dl by dA and then dA by dz. We will first find this dA by dz first, and this dA by dz just represents that we are going to find dA1 by dz1, dA1 by dz2, and so on, and similarly dA2 by dz1, dA2 by dz2, and so on down below as well, up till n and up till n. So we can write this dA by dz as dAi by dzj for all the different values of I and j. Now note that this ai depends on ezi, and in the denominator we will also be having dzi, and we will be also having dzj, and then the rest sum which does not include I or j. And also this del represents the partial derivative, so only this gz term will be considered as a variable, while the rest of these terms are going to be considered as just the constant. So when this j is not equal to I, then only this will be our variable, while the rest are going to be our constant values. But when this j will be equal to I, then this and this both are going to be the variable, while this won't be there and this will be considered as the constant. So we will be having two cases here, and the case one is where j is not equal to I, and the case 2 is when j is equal to I. And in both these cases this derivative are going to be different because the variables and the constant in this equation are going to change. So let's first find for this case. We can write this as dzi upon e power zj plus summation, where k is not equal to j. Now if you know the derivative, if f of x is equal to u by v, then the derivative of f of x will be given by v du by dx minus u dv by dx upon v square. So here this is our u, which is constant, and this is our v. So this is going to be this v term first, then the derivative of this, which will be 0, minus, and then the derivative of this denominator, which will be e power zj plus 0. So it will be just e power of zj, and here it will be squared as well. Now this denominator term can be written again in this form. So our final equations can be written as minus of e power zi. So this entire term I have just written back in this form, and as we had square, so I have taken it 2 times, and this will be ai while this will be aj. So finally we came out to be minus of ai multiplied by aj. So this is our value for del ai by del zj when I is not equal to j. Now we will find del ai by del zi when this is the case when I is equal to j, and in that case our derivative by again using this rule will come out to be, and computing these derivatives, and the derivative of this will be e power of zi plus 0, and once you multiply this inside, this and this will be cancelled, and this ith term can again be taken inside this summation. So we will have, notice here this summation is for k is not equal to I. For simplicity I have just omit writing this k equal to I, while this sum is the entire sum including I. So this will be our ai, and this can be written as 1 minus of ai, because if you take 1 minus of ai, then you will get, and this is the entire summation, and when you subtract the ith term from this summation, it will be just summation where k is not equal to I e power zk upon the entire summation. So this term is this term, which can be written as 1 minus of ai. So our del ai by del zi is given by ai multiplied by 1 minus of ai. So our final del ai by del zi came out to be minus ai aj when I is not equal to j, and ai multiplied by 1 minus of ai when I is equal to j. Now we can use this to find del L by del Z. Now similarly we will need to first find del L by del Zi for different value of I, and our loss can again be split into two ways, where we can first have this ith term with ai and the rest summation which does not include I for all k not equal to I, yk log of ak. So when we take the derivative, taking the derivative of this with this term will be having minus of yi upon ai, and then again the derivative of del ai with del zi, and here we will be having summation yk by ak, and this summation is for all k not equal to I. Here we will be having del ak by of del zi, but we already have these two terms from this equation. This is the case when I is equal to j, and this is the case when I is not equal to j. So we will just compute it, minus yi by of ai, and this term will be where I is equal to j, so it will be ai 1 minus of ai, and here the summation multiplied by this is minus, so this will be plus a k a I. A k will be cancelled and ai will be cancelled here. So it will be minus yi plus yi ai plus summation k is not equal to I yk ai. This ai can be taken outside, and this ai can be taken common from this. Now as this summation does not have ith term, we can include this I as well inside. So it will be, now here this y is the output, and if you remember in multi-class classification we give the output in the form of one hot vector. So one hot vector is 1 at any of the position while the 0 at the rest of the position. So this summation of yk represents the summation of this vector, and its sum is going to be just 1 because we only have 1 at one of the position. So finally we will have our final value as ai minus of yi, and this will be our del L by del Zi. And for different value of these I, we will be having same thing, and this we can continue for all the number of n neurons. In short, we can write this del L by del Z as a minus of y only. And if you remember, I skipped writing these 3 here. So this is del Z3 and this is A3 here, and this is y, which is the output vector. And this would be our final dz3 for one observation. And for all the observation, we can write this del cos by del Z3 as capital A3 minus of capital Y. And this will be our final D capital Z3. So our capital D Z3 came out to be A3 minus of Y, which was just the same for the binary classification as well. So all these equations that we had for the binary classification will be same for multi-class classification as well. So there's going to be no change in the equations, but only one thing will be different, and that is we will be using softmax activation function in the output instead of the sigmoid function, and our loss for the multi-class classification is also slightly different. So that's it for this video. We derived the equations for the multi-class classifications as well for the neural network. And in the next video, we will be implementing this in Python, and we will be making the application to recognize the handwritten digits. These digits are going to be 0 to 9. So we will be having 10 classes, and I am very excited to show you that. So let's move on to the next video, and I see you there.